Random variables temporal characteristics. So first, the question number one: A types of random variables. So there are so many types of random variables, but it is a 3 mark question. So I'm going to divide this random variables into two types: discrete random variables as well as continuous random variables. And discrete random variables have a cumulative distribution function, that is a continuous staircase function of x, and with jumps with a countable set of points. And in case of a random variable, it is also a cumulative distribution function wherever a sufficient smooth that it can be integrated from a non-negative function. Next, so in going to the question number 1b, ensemble average. So ensemble average and time average both comes under the mean, but there should be the mean is divided in two parts. One is ensemble average, second one is time average. So here the ensemble average formula is expected value z of x naught is equal to integral minus infinite to infinite z of x of naught p of z into dz, where x naught is the coordinate of a given point of a space axis, where p of z is a probability density function. Next, in question number 1c, the problem in which the x of t is a White-Sands stationary process with expected value of that x of t is given as 2 with a autocorrelation of 4 plus e power minus 0.1 into mod t. So find the mean and variance for the value of that s, which is varying from 0 to 1 of x of t into dt. So as we know that e of s is nothing but expected value of s. I am substituting this s value here, then it becomes, by integration all those we will get 2. This 2 is the value of mean. So in going to the variance e of s square formula, so variance of s is equal to e of s square minus e of s whole square. So already we have find out that e of s here. So now we need to find out that e of s square. So e of s square is equal to, the formula looks like this: integration minus 2 to t of t minus mod tau of autocorrelation of that function. So here the time period he given as 0 to 1 now, so that's why I am substituting that minus 1 to 1 here, and time period is 1 minus tau, and I am going to substitute this autocorrelation here. By integration all those things, we get the value of 200 into e power minus 0.1 minus 176. Now substitute this value in e power minus s, e power of e of s square, and next e minus e of s square is equal to 2 square, 4. This is the final answer. Next, going to 2a, this is also another problem. A random variable is defined with x of t is equal to a sin omega t plus pi, where a is a continuous constant and theta is a random variable uniformly distributed among the integrations minus pi to pi. Check x of t for a stationary. As I said that which is a stationary means that should be an independent of time. So since theta is a uniform random variable which is varying from minus pi to pi, as we know that the expected value of e of x of t formula minus integration minus infinite to infinite of x of t into dt. Now in the place of x of t I am going to substitute a into sine omega t plus theta into d theta, as a by 2 pi is a constant he taken outside. So by considering this expected value is equal to 0. Now you should find out that variance. So you should find out that autocorrelation. So we know that autocorrelation is nothing but expected value x of t plus tau. So by changing that we will get a 0. So both are independent with respect to the time. So we can conclude that it is a stationary process. Next. So in going to the 2b, what are the properties of an autocorrelation? So autocorrelation from a real value of a White-Sands stationary random process. Autocorrelation and spectral density from a Fourier transform, so is a pair, and autocorrelation is symmetric around 0. Why? Because that autocorrelation of the tau is an even function. So autocorrelation of tau is almost equal to autocorrelation of minus tau. Its maximum value occurs which is less than or equal to 0. And next, its value of the original equation equal to the average power of energy. As we know that energy form the E of x square of t is equal to integration minus infinite to infinite x square of t into dt. So in the place of that I am going to substitute directly that Sx f of Pf. Next, 2c, ergodic process. Normally ergodic is a stationary process. Equality of time properties and statistic properties. First order time average. So is defined by a power equation which is limit t tends to infinite 1 by 2t integration minus t to t x of t into dt. So mean periodic process is the mean square. So similarly the formula looks like this. And next in going to the main theorem. For a stationary random process x of t, if the ensemble average equal to time variable, it is called an ergodic. As I said in the earlier uh, question regarding that ensemble average, there should be two types of means will be there. One is ensemble average, second one is time average. For a stationary random process, if this ensemble and time average should be, if both are equal, then we can say that it is an ergodic process. And the formula is for this. For stationary, we can view that it is estimated with a mu of x. Next, for a random process, model noise, that is a random process source. How can we know it's a mean or variance? Answer is that should be depends upon the relative frequency, specifically by measuring the values of x of t from 1 to n. And calculating that average, it is the expected the time average which should be equal to the mean. Questions arise, will this time average be close to the mean if x of t is stationary? Okay, this is also another question which is going to be uh, for a stationary process, the mean mu of x of t is that should be independent of time. As I said, that stationary should be independent of time, otherwise it should not be a wide state by stationary process. Thank you and all the best for that.